Hey, welcome back to this series where we follow the LLVM tutorial for building our first programming language using LLVM. We're in the middle of the chapter 3, and at this point, we've written some code to generate the LLVM representation of several of the language elements, including variable references, numeric constants, binary operations. Now we're gonna work on the function code generation. So we also did that for a function call expression as well. But this time we're gonna generate the LLVM IR code for a function definition. So, and close out. So let's see how to do that. We're first going to generate the code, implement the CodeGen method for the prototype AST node. As a reminder, the prototype AST node means the signature of a function. So if you define a function, like I'm gonna define a function add, it's gonna add x and y together. Then the proto of the function is just that part. That's called the prototype of the function. For some reason, that's what they call it. I also hear it commonly referred to as the signature of the function. I like that name better. But anyway, in this tutorial, they call that the prototype of the function. And so we're gonna generate something that represents that in LLVM IR land. So let's copy this bit of code. So it's gonna return a function, whatever that is. It's pretty cool though that in LLVM IR there's a concept called function that we can just hook into, because clearly our language has a concept called functions. Okay. So what is this doing here? Whoops, I didn't mean to make a breakpoint. So what is this doing here? We're creating a vector that contains these pointers to types. Okay. So I think we want to represent the type of each argument or each parameter of the function. So like, as in, what's the type of x? We have to actually define the type of x and the type of y for LLVM IR before it's willing to do its job. So, and we said early on in the tutorial that this language only supports one type, and that's doubles. The double floating point numbers. So that's the type it's going to be for any number of arguments, and that kind of makes it easy. That's cool. So this is get double type. I think this is how you sort of instantiate a type. This probably just says set every element up to this size to that value. That's what I'm guessing this means. And then we're gonna also make a function type, it looks like. Function type, I bet you, is like the function signature. So this function type, probably it takes some parameters, but the first parameter is the argument list, the types of the argument list, which we already have figured out. And then, actually no, I think the second argument to this function type get is the types of the argument list, but the first one, I bet you, is the return type. And I guess the return type is always going to be a double. I don't know what this false means. Let me read this. The tutorial probably explains it. That this code packs a lot of power into a few lines. Love it. Note first that this function returns a function pointer instead of a value pointer, because a prototype really talks about the external interface for a function, not the value computed by an expression. It makes sense for it to return the LLVM function it corresponds to when CodeGen. CodeGen, that's a verb, clearly. The call to function type get creates the function type that should be used for a given prototype. Since all function arguments to Kaleidoscope are of type double, the first line creates a vector of n LLVM double types. It then uses the function type get get method to create a function type that takes n doubles as arguments, returns one double as a result, and that is not var arg. The false parameter indicates this. Oh, false means it's not var arg. Var arg means variable length argument list. So it does not take any number of arguments, is what false means. Cool. Let's write the next line and then maybe read the tutorial. Okay, I think my computer has calmed down, which is good. Let me double check to make sure it's still recording, because you never know. All right, it is recording. External linkage. Oops. The module. What the heck? Text editor is getting in my way here. Okay, the module :get. So what does this do? Well, we're gonna create a function based on this function type, and this external linkage, it probably means extern. Like, I didn't supply the definition, the definition of this function. All this is a function signature definition and the name of the function. So I bet you that creating this function then later on will allow this previous get function call over here, which is used by the function call expression to work. And then this module get, I guess it will put this function inside this module. That's my guess. Okay, so the final line above actually creates the IR function corresponding to the prototype. This indicates the type, linkage, and name to use, as well as which module to insert into. External linkage means that the function may be defined outside the current module and or that is callable by functions outside the module. The name passed in is the name the user specified, right? Since the module is specified, this name is registered in the module's symbol table. That makes sense. Okay. Now we need to set the names for all the arguments. Interesting. Okay, let's do that. Okay. How does this work? Oh, so this function apparently has these arcs already sort of like pre-populated, but they need names. Okay, I bet you these arcs are created based on the function type, because the function type said it had these many arguments, right? But we still have to go through and set the names for each arc. This arcs is referring to this arcs that was parsed during the parsing process. And then finally, we got our function. We're going to return it from this CodeGen method. Okay, got it. So this seems to make sense. Now, finally, let's write the CodeGen method for the function AST. So in the parser, we kind of split up a function AST into the proto part and the function part. And the function contains the proto part plus a body, which is an expression. So now we have just implemented the CodeGen method for the proto, but now we need to do that for the function. Okay, what's this first line doing? It's just getting the function based on the name the from the proto, but which it assumes has already been defined. Why can it assume that? If it doesn't, if it's not there, then we're gonna CodeGen the proto. Interesting. So maybe that function has already been defined. I don't know. Interesting. I'm not entirely sure how this logic works, but let me keep typing out this code first. So if we didn't actually get a function from the module, like we haven't already defined this function, then we're gonna lazily tell our proto to define the function, because we just wrote CodeGen code inside the proto to do that. So yeah, if it's not already defined, we're gonna define it essentially. But if even after that, we still don't have a function, then something really wrong has happened, and we're just gonna return a null pointer. You know, when in doubt, return null pointer, and then if the function is empty, I don't even know what that means. Function cannot be redefined. I'm gonna error out. I'm gonna just call my generic log error function. Say function cannot be redefined. I don't really understand why. Let me read the tutorial, see if it'll explain itself. For function definitions, we start by searching the module symbol table for an existing version of this function, in case one has already been created using an extern statement. So like, okay, I got it. So maybe like you had an extern statement, I don't know, there's a distance function that takes x, y, x2, y2 or something, and then you're trying to define another dist function, and then blah blah blah, and then it'll find the first one, the previous one that was that was defined, and so you're not gonna try to do that again. But okay, interesting. If module get function returns null, then no previous version exists, so we'll CodeGen one from the prototype. In either case, we want to assert that the function is empty, that it has no body yet. So okay, so we at this point the function empty means the function has no body yet. We're gonna define it, but if it already has a body, that's a problem because we don't want to nuke what it already has. So we error out and say we cannot redefine it. But if it's not empty, if it is empty, then that's good. We're gonna define what the function has now. Great. So that's the next step. So we're gonna do basic block bb, 1 star, not 2. Basic block : create the context entry the function builder dot set insert point bb. What does this mean? Named values dot clear. Why are we clearing the named values? This doesn't make sense. Record the function arguments in the named values map. But why are we clearing it? What? Like, what if another function declared some named values and now that's gone, right? What's going on? Okay, so why are we doing this? Let's read. Let's read to get an explanation. Now we get to the point where the builder is set up. The first line creates a basic block. That's I imagine that's like the code block, which is inserted into the function. So we're gonna create a basic block. This is the function reference to tell it to insert it into. The context is just a global context. That doesn't matter that much. Entry, I don't really know why we call it entry. I guess we just name the block. We have to give the block a name. We're gonna name it entry. So there's the block. We're gonna set insert point. What does that mean? The second line then tells the builder that new instructions should be inserted into the end of the new basic block. Oh, okay. Interesting. Oh, okay. So the new instructions, by new instructions, I think it means whenever it's doing stuff like builder.create call or builder.create fadd, builder.create fsub, etc. that has to get inserted into this graph. This is kind of like jQuery chaining, actually. It's weird to relate it to jQuery, but that's kind of like, so the insert point is like stick it into this subtree. So like you in jQuery, right? Why am I explaining this in terms of jQuery? But in jQuery, you might do something like, hey, I want to select this element with the ID of thing, and I want to like do a whole bunch of stuff to it. Maybe like I don't know, add a class to it. Blah blah blah. I want to change the attribute, etc. And then, so all of these instructions apply to the subtree which is started by that thing. But, you know, if we didn't do that, if we just started at the top of the document or something, then the insert point is at the document, or maybe document.body would be more correct. So the insert point is like the current point within the tree that all of these create statements are going to go into. And here we're saying we created this function that looks like this, and we just created this function block. We're gonna call this entry, and insert point is here. So whenever you're gonna create a statement, create whatever, the thing that gets created gets inserted in here. So that's what set insert point is doing for us. Record the function arguments in the named values map. Okay, so I wrote this code already. Let me get an explanation for it. Basic blocks in LLVM are an important part of functions, right? That we define the control flow graph. Since we don't have any control flow graph, our functions will only contain one block at this point. We'll fix this in chapter 5. Next, we add the function arguments to the named values map after first clearing it out. That's so that they're accessible to variable expr AST nodes. Why do we clear it out? That's the part I'm confused about. Okay, we'll figure that out later. Okay, next, we add the function arguments to the name value maps. Yeah, we already read that. Okay, the next part is this. All right, let's type that code in. There's a lot to this. If the value ret val, I prefer to do this as a separate line. Okay, so if we CodeGen the body and we got something back that's not null, then we're gonna say builder.create reach. That's a return value, I bet. It's like a return statement. And then we're gonna verify the function. Okay, it's interesting that we need to verify the function. I don't know how we do that, but that makes sense to me. So whatever is currently the body of the function only has one expression in it. We're gonna CodeGen that expression, and then whatever the value is, we'll use that in the return statement. Okay, so once the insertion point has been set up and the name value map populated, we call the CodeGen method for the root expression of the function. Excuse me. And if no error happens, this emits code to compute the expression into the entry block and returns the value that was computed. Assuming no error, we then create an LLVM ret for return instruction, which completes the function. Once the function is built, we call verify function, which is provided by LLVM. Oh, we didn't have to write that. This function does a variety of consistency checks on the generated code to determine if our compiler is doing everything right. Using this is important. It can catch a lot of bugs. Once the function is finished and validated, we return it. Okay. We error reading body remove function. What? No. I guess. Oh. I see. If we didn't successfully get a body to CodeGen, then we actually want to erase, like clean up everything that we made. Erase from more or less. And then return a null pointer. Okay. Only piece left here is handling of the error case. For simplicity, we handle this by merely deleting the function we produced with the erase from parent method. This allows the user to redefine a function that they incorrectly typed in before. If we didn't delete it, it would live in the symbol table with a body, preventing future redefinition. If this code does have a bug though, if function AST CodeGen method finds a existing IR function, it does not validate its signature against the definition's own prototype. This means that an earlier external declaration will take precedence over the function definition's signature, which can cause CodeGen to fail. For instance, if that makes sense. But what it's saying is that if you, kind of the scenario I actually already laid out before. If a CodeGen F, it takes X, for example, but then you want to later on redefine F with a different parameter list. I think there's no comma. Then this case will fail because it will actually use this signature of the function, but with a body that's defined in here. Maybe it returns x plus y times z, I don't know. And then there's going to be inconsistencies. I think that validate function will error out probably when you do this. Anyway, so driver changes and closing thoughts. So for now, code generation to LLVM doesn't really get us much, except that we can look at the pretty IR calls. So let's look at those pretty IR calls. So this sample code inserts calls to CodeGen into the handle definition, handle, extern, etc. functions, then dumps out the LLVM IR. This is a nice way to look at the LLVM IR for simple functions. For example, you can use this REPL now. Type in an expression, it'll show you the LLVM. Let's actually get it to do that though. So we'll have to steal that from the full code listing, because they didn't actually show that as part of the tutorial, strangely. But I think the only part we need to grab is these three handle functions: handle definition, handle extern, and handle top level expression. I am a little bit surprised that it didn't explain this, because this is gonna give us I guess it's gonna get the result of parse definition and then call CodeGen on it to get an IR form of the code, and then we can actually print it. Oh, the IR form of the code has a print method. Why are we giving to print this errors thing? I have no idea what that is. But in any case, we can print it. So let's steal these three functions, stick it in our code. I'm gonna replace those same three functions, which came from the previous chapter. Replace them with these, and hopefully it can build. I don't know if it can, but I'm gonna call my build script, which will attempt to build it. And that did not work. Use of undeclared identifier builder. 20 errors generated. Let me look at my build script. First of all, I think, their build command has these extra stuff in it, so I'm gonna use this. So this is the command that I used to build their version of the code, so I'm gonna steal from it. Probably I used G++. I think that's the same as Clang++. Not 100% sure though. So I'll try to match my build command to their build command. Still no luck. Try to change this to Clang++. Maybe that makes a difference. Nope. Okay, I'm gonna need to debug this. So I'm gonna do a just do a visual comparison of what I have versus what they have. Hopefully that can give me some hints as to what the problem is, because I think building their code with this command does work. I have tested it last night. With all of these warning, but it does work. So now my code does not have some of these includes. Maybe they are needed, so I'm gonna try adding them in. This algorithm CC type CS standard IO CSC standard lib. Okay, I'm gonna try it. Oh, we're using namespace LLVM. That's a biggie. Do we need that? Maybe we need that. I bet we need that. Okay, let's do using namespace LLVM. Still 20 error generated. Use of undeclared identifier the context. Oh, okay. I think this is just a where I declared the thing. So I'm gonna move these guys to the top. I have to define it before code actually tries to use it, is what it is. So perhaps I'll have this static global variables all the way at the top together. These are for the parser and lexer, and these are for the CodeGen. Okay, now I'll try to compile it. Still 20 errors. Too many errors, but we did get rid of that first error. So out of line definition of CodeGen does not match any declaration in variable expert AST. Oh, I see. I think I know what this is. I did not see how okay, I'm gonna close their code for a moment. See how in here for the number expert AST, I actually had to write repeat this definition of the CodeGen method in the body of the number expert AST class, and I actually didn't do that for the other subclasses. So I think I actually have to do that for every subclass. I'm just gonna copy it to every subclass. Okay, and I think I just did that. So let me try compiling it again. $15 errors. Yes, the list is actually tractable now. It didn't say too many errors. Oh man, it's not too many errors. It's just the right number of errors, just the right amount of errors. Okay, anyway, log error, use of undeclared identifier. I bet I just need to move, like have a forward declaration of log error is probably what I need. Yeah, or I can just move this whole thing on to the top. Actually, that's what I'm gonna do, or near the top. 11 errors. Okay, getting smaller. I cannot return the thing that's supposed to be void, right? 178. So so here I'm just deviating from the tutorial, and that's the difference. Ten errors. E is not declared. 209. Oh, a lot of these errors are coming from 209, so we can probably kill a lot of them with one shot. E has not been declared. What? Like, what is this E equals here? Not that E. This E. E equals args dot size. They didn't declare E either. What the heck? Where is E? Oh, this is comma. This is a comma, not a semicolon. I think that makes a difference. Oh, this E is unsigned. So, I see. This is a variable declaration list that declares first I and then E. Okay. That will probably fix it then. Only 4 errors left. Okay. Return type of out-of-line definition of prototype AST CodeGen differs from that in the definition. 232. It is saying, oh, okay. Yours is saying that, hey, you said it's a return a value, but value pointer, but it actually returns a function pointer. Okay, fine. Let's make them match. I hope that works, because the super class actually said it's a value pointer. Even though a function, I assume, is a subtype of value. That did fix it. We only have 2 errors left. 239. The error is demodule is not a class namespace or enumeration. Demodule is declared over here. Okay. Demodule. Right, we declared demodule over. I just copied this code, man. It is a unique pointer to a module. So the line is complaining about is 239. Let's go back there. And this line, it looks like function : create. Oh, it's demodule dot get, not demodule : get. Okay. One last error. Okay. So this one, is similar to a previous one that I fixed. This returns a function pointer on 262. And so I just need to make the signature match over here. And it built with all of these errors. That says my, like, the version of the library it was compiled for is newer than my Mac. It's basically saying my Mac is old. I'm gonna ignore those warnings. I think it was successful in building my binary program. So at this point, I have this REPL. Let me make the font size a little bigger. I have this REPL now, and I can type expressions in the language within the REPL, a semicolon, and when I hit enter, it's 6 volts. No. Dang it. No. Oh, man. It's 6 volts. Oh man, this is gonna be a painful, or potentially it could be a painful bug hunt, actually. Let me think. Well, this session has gone on, so I'm gonna stop this video short. The good news is we figured out how to build the program. The bad news is it has a SIG fault. We will need to use some debugging techniques, I think, to get to the bottom of the SIG fault. But yeah, I'm gonna end this video here, and I'll see you on the other side.